Imagine if instead of typing lines of text on a screenwriting software required you to like physically bend steel.
Right.
I mean, imagine if building a computer program was less like writing a step-by-step recipe and more like welding together this physical labyrinth of pipes where the sheer geometry of the metal dictated exactly where the water could flow.
It's a completely wild visual. Yeah.
Welcome to today's deep dive. Because if you have ever felt the lag of a computer loading a massive spreadsheet or, waited forever for a video game to patch, you have experienced the fundamental bottleneck of how we currently build our digital world.
We all have, yeah.
Today, we are looking at a system that literally treats software as physical geometry.
It is a radical departure from everything we've been taught about computer science, honestly.
Totally.
For the last 70 years, we've operated on this assumption that software is linguistic right. It's a list of textual rules that a processor has to read and interpret and then execute step by step. Today, we are exploring a framework that just shatters that paradigm entirely.
Yeah, and the source material we have in front of us today is the architectural documentation and the README file for a system called Gnosis.
Which is fascinating.
It really is. The creators describe Gnosis as a graph-first language and toolchain. But to be completely honest with you, as I was reading through this, it felt way less like a software manual and more like a textbook on quantum mechanics or applied thermodynamics.
I had the exact same reaction.
Right, because we are going to be talking about things like racing compilers and amplituhedron data geometry and this universe kernel that literally enforces the speed of light within the code itself.
Which just sounds like sci-fi.
It does.
Yeah.
But my mission for you today is to decode this absolute architectural marvel. We're going to figure out how abandoning traditional programming allows this system to achieve speeds that shouldn't even be like physically possible.
I am thrilled to dive into this with you, because when you look closely at the architecture described in these documents, it isn't just some iterative update to how we build web servers. It is a fundamental reimagining of computation. It basically takes the guesswork out of software engineering and replaces it with pure mathematical certainty.
Okay, let's unpack this. Before we can even begin to talk about how Gnosis serves millions of requests per second, we have to understand the basic building blocks. Because as we established, you don't write lines of code in Gnosis.
No, you don't.
You build what the documentation calls a topology.
Yes. The core architecture is built around this concept that every Gnosis program, which is saved as a .sig file, by the way, is a directed graph.
Right.
In traditional programming, when you write code, the compiler turns your text into something called an abstract syntax tree, or an AST for short.
Let's pause right there, actually, because I want to make sure we were all on the same page. For anyone listening who isn't a compiler engineer, what exactly is an abstract syntax tree, and why is it such a bottleneck?
Think of an AST, like a massive, complex decision tree.
Okay.
The root of the tree is your main program, right? And the branches are your if-then statements or your while loops, and the leaves are the actual variables and actions.
Makes sense.
So when your computer runs the program, the processor basically has to walk down this tree. It hits a branch and has to stop and evaluate a condition like, is X greater than Y?
Right.
And then it decides which branch to take. That evaluation takes time. It requires memory lookups. It requires the CPU to guess which way the branch will go, which is something called branch prediction. And if it guesses wrong, it has to throw away its work and back up.
Wow, so it's inherently sequential.
It's inherently sequential and inherently prone to friction, yeah.
So it's like navigating a maze by walking up to every single intersection, pulling out a map, reading the instructions, and then making a choice. What does Gnosis do instead?
Gnosis throws the AST away entirely.
Just gets rid of it.
Gone. It provides exactly 6 primitive ages, and that is it. Every program is just a combination of these 6 structural primitives.
I actually have the list right here. It's fork race, fold vent process, and sliver. Now, I have to push back on this because when I saw this list, I genuinely didn't understand how it could work.
It's unintuitive at first, yeah.
Where are the if-then statements? How do you write software without conditional logic? I'm thinking about this like, instead of giving someone a map and asking them to navigate a maze, it's like dropping a gallon of water onto a giant vertical pegboard.
That's a great way to picture it.
The water doesn't read instructions right, it just flows through the physical layout of the pegs.
Yeah.
It naturally forks, it races down different paths, and it drains out where it's supposed to.
That is the perfect analogy. The water doesn't ask questions. It just flows where the geometry allows it to flow.
Okay.
Let's look at the race CE and vending mechanics specifically to see how this works in practice. When the data hits a F4K primitive, The execution literally splits into multiple parallel paths.
It just duplicates, essentially.
Right. Then those paths might race C. In a standard programming language, if you want to run multiple tasks at the same time, you have to spin up multiple threads, and then you have to write very complex, error-prone logic to manage them.
Which is a nightmare.
It is. You have to tell the computer, okay, wait to see which one finishes first, and then safely shut down the others without crashing the memory.
Right, which usually leads to massive headaches like race conditions or deadlocks where two pieces of code are waiting on each other forever.
Exactly.
Yeah.
But in Gnosis, the race primitive simply means the first path to complete its geometric flow wins. And here's a mechanism that makes it brilliant.
Okay.
The loser of the race isn't just ignored. It is aggressively and instantly vented via the vent primitive.
Vented, like opening a release valve on a steam pipe.
Precisely. The vent primitive prunes the losing path instantly. And the source document is very specific about the physics of this. The pruning propagates down, never across.
Wait, why does that matter? Down versus across?
Because if a system tries to kill a process by reaching across to another thread, you run into those locking issues you just mentioned.
Oh, I see.
The system has to pause, check the state of the other thread, ask for permission to alter its memory, and so on. By ensuring that the vent only propagates downward through the graph, it ensures that execution resources are freed up instantly, purely structurally.
So you aren't writing logic to manage the threads at all?
No, you aren't. The geometry of the race E and vent primitives inherently resolves the execution state. It is a physical certainty, not a logical condition.
Which brings us to a term in the documentation that completely melted my brain, the octonionic compiler.
Oh yeah, this is dense.
Very. The source says that Gnosis abandons associative AST control flow entirely. It routes execution physically by breaking mathematical associativity mapping operations to something called the Fano plane.
Right.
Now, I know we are knocking on the door of some incredibly dense math here, but we have to open this door. What does it mean to break mathematical associativity, and what on earth is a Fano plane?
Let's break it down mechanically. Mathematical associativity is a property you learn in grade school. It says that when you are adding or multiplying numbers, the grouping doesn't matter. So A plus B calculated first and then plus C is the exact same as A plus the result of B plus C.
Right, it equals the same thing.
Standard software relies heavily on this. It allows the compiler to shuffle things around and optimize the tree.
Yeah.
But the octonionic compiler in Gnosis does the opposite. It intentionally uses non-associative algebra.
Meaning the grouping does matter. If you do A and B first, it fundamentally changes the physical outcome compared to doing B and C first.
Exactly. And they map these operations onto the Fano plane, which is a geometric concept from finite math that illustrates the multiplication rules for octonions.
Octonions?
They're a type of number system that is inherently non-associative.
Okay, but why? Why take away the flexibility of standard math?
Because flexibility requires decision-making, and decision-making requires time.
Oh, wow.
Right. By mapping the operations to a non-associative space, the system is removing the CPU's ability to choose. There was only one valid geometric path for the computation to flow.
So the processor isn't pausing to ask, should I execute this branch or that branch?
Exactly. The geometry of the Fano plane dictates the absolute boundary of the execution. The shape itself is the computation.
So if I'm a developer, this requires a total rewiring of my brain. I can't think in linguistic logic anymore. I can't say if the user is logged in, show them the dashboard.
No, you can't.
I have to think in geometric traffic flows. I have to build a topology where the data forks, races against an authentication process, folds back together, and vents the unauthorized exhaust.
It really is civil engineering. You are building data aqueducts.
And when you build an aqueduct instead of writing a maze, the performance benefits are staggering. Because there is no AST traversal and no engine loop constantly checking what instruction comes next, a Gnosis topology compiles down to a flat, unadulterated chain of functions.
And the speeds they get from this are wild.
I was looking at the performance numbers they cited, and they sound almost fake. They claim this ahead-of-time compiled topology achieves 176 million executions per second.
It's hard to even conceptualize that.
That means a single execution takes about 6 nanoseconds.
To put 6 nanoseconds into perspective, light itself only travels about 6 feet in that amount of time.
That is insane.
It is approaching the absolute theoretical speed limits of the silicon hardware itself, simply because the software no longer has to think. The path is already forged in the metal.
Okay, so we've established that the code is essentially a physical racetrack. But that naturally leads to the next question, who is building the racetrack and who is driving the cars?
Right.
Because in standard programming, You write your code, you push a button to compile it, the compiler translates it into machine code once, and you're done. It's a single static process.
Usually, yes.
But Gnosis unleashes what the document describes as a literal swarm of compilers that race against each other on every single input.
This is where we move from fluid dynamics into evolutionary biology. The architects of this system didn't just build one compiler, they built a family of them.
A whole family.
And they don't just pick one to compile the whole program. They allow these different compilers to fight for dominance at every single node of the topology.
Okay, I want to go through this family because they actually gave them names, and each one has a specific personality or optimization strategy. Let's start with Lilith.
Lilith is described as the fastest compiler on Earth.
Okay.
The underlying mechanism is that Lilith is written in C and uses a forward-only scanner with zero backtracking.
So no second guessing, it just sprints through the code and translates it.
Exactly. Because it never looks back to reevaluate it, it can compile a topology in just 3 microseconds. And the output is incredibly lightweight. It can be distributed as a tiny 5.6 kilobyte WebAssembly file.
Wow.
Lilith is pure, unadulterated speed.
But speed isn't everything, right? Sometimes you need a smaller payload rather than a faster compile time, which is why Lilith has an anti-parallel pair named Eve. What does Eve do?
Eve utilizes a mechanism called the Worthington whip.
The Worthington whip.
And while Lilith focuses on compilation speed, Eve focuses on extreme output compression. It takes their data chunks, forks them into a race between different compression algorithms like gzip, Brotli, and deflate, and mathematically guarantees the smallest possible output.
And how small are we talking?
The documentation notes that Eve can take a batch of 1,013-byte chunks, there's 13,000 bytes total, and crush it down to just 61 bytes.
Wait, 61 bytes from 13,000?
Yes. That is a 98% reduction executed in fractions of a microsecond.
That is absurd. Then you have Becky written in Rust, which is noted as the fastest globally on every topology. You have Betty written in TypeScript, which is the deepest compiler running through 13 rigorous verification phases to ensure the math is flawless.
Right.
And then there is Betty with an I, which honestly sounds like a paradox. It says Betty is self-hosted and reads its own betty.jig topology to drive its execution order. How does a compiler compile itself?
It is a concept called bootstrapping. Essentially, the Betty compiler is written in the Gnosis topology language itself.
Oh.
So to run Betty, you feed the Betty compiler its own source code. It uses its own geometric rules to figure out how to compile itself. It creates a perfect loop of self-reliance.
Now I have to play the skeptic here. I hear all of this, and my first thought is, isn't running 6 different compilers simultaneously on the exact same input a massive waste of CPU power?
It's a common criticism.
It sounds to me like hiring 6 different taxi drivers, putting them all in separate cars and telling them to drive you to the exact same destination just to see who gets there first. Why not just benchmark them, figure out which compiler is the overall best, and just use that one permanently? Why burn the energy?
What's fascinating here is that your question touches on one of the most profound mathematical limitations of computer science.
Really?
Yes. It's the distinction between local optimality and global optimality. The creators of Gnosis reference a formal mathematical proof in the documentation called optimality undecidable.lean.
A mathematical proof? So they didn't just guess they proved it. What does it prove?
It formally proves that global optimality is undecidable, meaning it is a mathematical impossibility to find one single compiler or one single strategy that will absolutely be the fastest and most efficient for every possible input across every possible hardware state forever.
Because things change.
Right. The variations of data network latency and memory availability are practically infinite.
So searching for the one perfect compiler is just a fool's errand.
Exactly. The ceiling of provable knowledge is local optimality. That means finding the best path for this specific piece of data at this exact millisecond under these exact hardware conditions.
Okay.
Because you can never prove that Lilith or Becky will always be the best modal. Gnosis doesn't even try to pick a permanent winner. It runs a swarm.
It runs all of them.
It uses a mechanism called the sliver, which is the +1 primitive we mentioned earlier, to guarantee that every strategy survives the race.
Wait, so if Lilith wins the race for a specific node, what happens to Eve and Becky? Are they just killed off?
They are vented for that specific execution, freeing up the memory. But the strategy itself, the compiler identity, is preserved via the sliver primitive. They live to race another day on the next node.
And this leads to a concept in the documentation that I found incredibly poetic. It's called the void boundary.
I love this concept.
During what they call the forest passes, which are basically iterative practice runs the system uses to map out the topology, the system generates thousands of rejections. The document specifically cites 11,016 total rejections across 9 passes. This rejection history is the void boundary.
Yes, it is a permanent physical ledger of failure.
Think about how profound that is. The system isn't just learning the right way to do things, it is meticulously mapping out the exact shape of what doesn't work.
Exactly.
It encodes those failures as a physical boundary that the code knows never to cross again. The text mentions the kernel gap. It defines this as the distance between the provable local optimality, the best we can do right now, and that undecidable global optimality, absolute perfection. The gap is finite. It shrinks as the void boundary grows, but it is never provably zero.
If we connect this to the bigger picture, it's almost a philosophical statement on the limits of knowledge encoded directly into a web server.
It really is.
We could always inch closer to perfection by meticulously cataloging our failures, our void boundary, but absolute universal perfection is a mathematical impossibility.
And to show how deeply this philosophy is baked into the actual code, the source points out something wild about those forest passes. It says that the void boundary nodes, the parts of the system tracking the failures, consistently converge to use a different compiler than the data path nodes.
The observer is compiled differently than the observed.
It's like the Heisenberg uncertainty principle applied to software compilation. The physical act of measuring the failures requires a fundamentally different geometric structure than the act of processing the successful data.
It demonstrates that the swarm is truly adaptive. It doesn't use a hammer for every problem. It optimizes the architecture of observation independently of the architecture of execution.
Okay, so we have this swarm of compilers racing each other, constantly probing the void boundary, trying to find the absolute fastest path. But if Lilith is solely focused on winning the race, what stops her from cheating?
What do you mean?
Like, what stops a compiler from just bypassing a crucial security check or ignoring a data validation step just to shave a nanosecond off the execution time? In standard software, you catch bugs by writing unit tests. But Gnosis uses something called ambient law.
This is perhaps the most rigorous aspect of the entire Gnosis ecosystem.
Okay.
In traditional software development, as you said, we rely on empirical testing. You write a program, you pump 1 million simulated requests through it, you measure the time, you say, okay, our throughput is roughly X requests per second.
Right. And if it doesn't crash, you assume it's safe.
Exactly.
Yeah.
But Gnosis rejects empirical testing entirely.
It doesn't run benchmarks.
It benchmarks the reality, but it doesn't rely on benchmarks for its core guarantees. Throughput, resource bounds, and security are mathematically proven theorems.
The document names a specific theorem, actually. It's called Theorem Server Optimality. It claims Gnosis is the first web server in history whose throughput bound is a mathematical theorem.
Yes.
Now, you brought up TLA Plus and Lean 4 earlier. What are these, and what does it mean to have a mechanized proof for a server?
Lean 4 and TLA Plus are formal specification languages. They're used in aerospace engineering and microprocessor design.
Oh, so high-stakes stuff.
Very high stakes. Instead of running a test to see if a program crashes, you write out the logic of the program as a series of mathematical equations. A theorem prover then analyzes the entire mathematical universe of possible states for that program.
Wow.
The documentation states that Gnosis has 14 mechanized proofs for its critical path, make span, and Pareto optimal resource usage.
Let's translate those two terms. What is a critical path make span?
The critical path is the longest sequence of dependent tasks that must be completed to finish a process. Make span is the total time it takes. Okay. By mathematically proving the critical path make span, they have essentially proven that no other scheduling algorithm in the universe could possibly execute that specific graph of tasks faster.
And Pareto optimal resource usage.
Pareto optimality is an economic concept. In this context, it means the system is in a state where it is impossible to improve the speed without adding more hardware workers, and it is impossible to reduce the hardware workers without slowing down the speed.
So it's perfectly balanced.
It is mathematically locked at the absolute theoretical limit of efficiency.
I am thinking about this like the difference between testing a physical bridge. The traditional software way is to drive a fleet of heavy trucks over the bridge 100 times. If it holds, you say the bridge is safe.
Right.
The Gnosis way is to use physics and chemistry to prove mathematically that the molecular structure of the steel itself literally cannot collapse under that exact weight.
That's a perfect way to describe it.
One method gives you high confidence, the other method gives you absolute immutable certainty. And Gnosis enforces the certainty through something called the universe kernel.
The universe kernel is the enforcer of ambient law. The documentation makes a point to say that the system fails closed.
Fails closed, meaning what?
Before any compiled topology is allowed to actually run and process data, it must be admitted by the shared God formula V1 universe kernel.
What happens if Lilith tries to submit a compiled topology that skips a security check to go faster?
If the compiled graph violates even one of those 14 mathematical proofs, the universe kernel simply rejects it. It doesn't throw an error code or a bug report. It literally will not admit the topology into existence. It treats the bad code as a violation of physical law.
And speaking of physical law, it actually uses literal physics as programming constraints.
It does.
The universe kernel has built-in observables like law.status and law.deficit, but it also includes explicit physics constants natively in the language. The speed of light, the Planck constant pi, the gravity constant.
It's incredible.
There are native formulas for Landauer heat, which is the minimum amount of energy required to erase a bit of information, and photon energy. Why does a web server need to know the Planck constant?
This raises an important question about where computing is headed. The document notes that most applications remain dimensionless. By contract, meaning a simple to-do list app doesn't need to care about the speed of light.
Right, of course not.
But Gnosis provides these constants because it is preparing for a world where computation is so densely packed and so impossibly fast that the physical limits of hardware thermodynamics and the actual speed of light over fiber optic cables have to be accounted for in the software's architecture itself.
That is mind-blowing.
You can actually attach a quantum dimension to a data literal.
So if everything is governed by this mathematical ambient law, how does that change network security? The document mentions that the native guest path preserves caller authority using UCAN and ZK envelopes rather than flattening it. What is a ZK envelope and how does it secure the border of this system?
ZK stands for zero knowledge. A zero-knowledge proof is a cryptographic method where one party can prove to another party that they know a specific piece of information without actually revealing the information itself.
Give me an analogy for that.
Imagine you need to prove to a bouncer that you are over 21, but you don't want to show him your ID because you don't want him to know your name or your home address.
Makes sense.
A zero-knowledge proof is a mathematical way of handing the bouncer a cryptographic certificate that irrefutably proves your age is greater than 21 without revealing a single other piece of data.
Okay, so a ZK envelope wraps the incoming request.
Yes. In traditional middleware, a request comes in, the server strips off the security credentials, checks them against a database, and then passes the request along as a flattened internal task.
Which creates vulnerabilities.
Right, exactly. It creates vulnerabilities inside the network. In Gnosis, the authority is preserved in the envelope. Because the universe kernel enforces ambient law, the topology physically cannot admit a request that doesn't carry the mathematically proven authority to enter.
So what does this all mean?
You don't need a bloated firewall, checking permissions at every step. The geometric shape of the door literally will not fit the shape of an unauthorized key.
And the document actually provides a real-world example of this mathematical enforcement in action with the MOE transformer benchmark shootout. They ran two variants of a highly complex machine learning routing algorithm.
I read about this.
The regular transformer algorithm passed the 14 formal proofs, the universe kernel admitted it, and it ran flawlessly, but then they tried to run the MOA variant.
And the MOA variant had a structural flaw. It attempted to route data in a way that violated the mathematical bounds of resource usage.
And the result was that it was instantly correctly rejected by universe admission. It didn't start running and then crash halfway through corrupting memory. It was barred from existing in that universe because it failed the math test.
Exactly. It guarantees stability at the border.
Okay, so the execution is math, the security is math. Let's talk about the data itself. Because if Gnosis relies on pure geometry to enforce its rules, it takes the exact same extreme approach to how it stores and reads information.
It does.
The documentation reveals that Gnosis completely abandons standard data parsing formats like JSON or XML.
Traditional parsing is one of the most computationally expensive things a computer does.
Why is that?
When a system receives a JSON file, The processor has to scan through it sequentially. It has to read it character by character, looking for open brackets, quotation marks, colons, and commas, just to figure out where the actual data lives.
It's linear. It's like trying to find a specific sentence in a book by starting at page 1 and reading every single word until you find it.
Precisely. And in a high-performance system, that linear scan is a massive bottleneck. Gnosis introduces several new formats to bypass this. The first is not the global network optimized tree. This is a binary native format. The documentation shows it provides a 25% reduction in wire size simply because it strips out all the textual formatting overhead required by JSON.
And for systems that need even more extreme compression, they have the bitwise or DNA format. This packs data points into just 2 bits of memory, achieving a 75% size reduction.
Which is huge.
The source notes this is specifically designed for high-throughput telemetry like a sensor, sending thousands of pings a second, where you absolutely cannot afford the CPU tax of compressing and decompressing complex formats.
But those are just warm-ups, honestly.
Really?
The most radical format, the one that truly realizes the vision of software as geometry, is the amplitude. It uses the .NOT file extension.
Here's where it gets really interesting. The amplitude completely replaces the abstract syntax tree we talked about earlier, and the source makes a claim that stopped me dead in my tracks.
About the file size.
Yes. It says that an entire .NOT file is exactly 28 bytes, and that is a fixed size regardless of how complex the algorithm inside it is.
It sounds impossible.
It does. You could have a simple script to add 2 numbers together, or you could have a sprawling machine learning model with 1 billion parameters, and the file that defines its structure is exactly 28 bytes. How is that mechanically possible?
It requires a complete shift in how we think about storing instructions. They achieve this fixed size by using 4 geometric scalars that define the boundaries of a static Grassmannian tensor.
Okay, stop right there. Grassmannian tensor. Unlock that door for me. What is that?
In linear algebra, a Grassmannian is a mathematical space that parameterizes all linear subspaces of a certain dimension. Let's simplify that, though.
Please do.
Imagine you have a 3D room. A Grassmannian can mathematically describe all the possible flat 2D planes that could slice through the center of that room. A tensor is just a mathematical object that holds multiple values together, like a multidimensional array.
Okay, so I'm thinking about this like, instead of storing a high-resolution image of a perfect circle by saving the color of all 4 million pixels individually, which takes up megabytes of space, you are simply storing the mathematical equation of the circle.
Yes.
Like x squared plus y squared equals radius squared. You aren't saving the drawing, you are saving the geometry that creates the drawing.
That is exactly what is happening. An AST stores the million individual steps of the program. The amplitude only stores the 4 coordinate scalars that define the geometric space of the program.
And because it's just 4 coordinate numbers, it's always exactly 28 bytes. But how does the computer actually execute that? It can't just run an equation, it has to process the data.
This is where Gnosis uses what it calls a topological raycaster.
A raycaster.
Instead of linear memory parsing, reading the book word by word, it uses a technique called Schubert slicing.
Okay, Schubert slicing. What are we slicing here?
We are geometrically intersecting planes because the program is now defined as a mathematical space. Finding the next instruction isn't a matter of reading down a list. It is a matter of mathematically projecting a ray through that space and finding where it intersects with the data you need.
So instead of scanning 1 million cells linearly, the math equation just instantly pinpoints the exact 3D coordinate of the data.
Yes, and the performance difference is staggering.
Let's hear it.
The text compares standard linear memory parsing in V8, which is the JavaScript engine inside Google Chrome and Node.js, to the Gnosis Wessam topological raycaster. When V8 tries to search through 500,000 cells of data, sequentially it takes 120 milliseconds.
Which is noticeable lag to a human.
Exactly. The Gnosis raycaster, using Schubert slicing to project the data geometrically, finds the answer in 1.43 milliseconds.
Whoa.
That is an 84 times speedup achieved entirely by changing how the computer looks at the data.
And this leads to a concept that the document emphasizes heavily. Big O of 1 load times. For our listeners, what does that mean practically?
Big O notation describes how the time to run a process scales as the amount of data grows. Big O of n means the time scales linearly. If you double the data, it takes twice as long to load.
Right.
Big O of 1 means constant time. It does not matter if the amplitude represents a graph with 10 edges or 100 million edges. Because the raycaster uses Schubert slicing to instantly project the volume based on those 28 bytes, the load time is identical.
The load time does not scale with complexity. The source measured the size reduction at 49,604 times smaller than equivalent legacy AST sequences. I want you listening to really think about the daily applications of this. Imagine loading a massive AAA video game or a terabyte-scale AI model into memory.
Usually takes forever.
Normally, you have to sit there watching a progress bar as the computer reads all the initialization files linearly. With an O of 1 amplitahedron, you could theoretically load the entire geometric boundary of that massive program into memory instantly.
It eliminates the concept of parsing time. The data is just ready.
Okay, so we've squished the data into 28-byte geometries. We're computing it in nanoseconds using racing compilers, but none of that matters if it gets stuck in a traffic jam trying to talk to the network.
Very true.
How do you physically transmit a geometric amplitahedron over the internet? This brings us to a concept Gnosis aggressively calls prismatic refraction.
Yes. The wire protocol of Gnosis operates on a profoundly counterintuitive motto. The documentation literally says vomit bits as fast as possible and let geometry figure out the shape.
Which sounds completely unhinged.
It does.
When I read that, I was incredibly skeptical. If I understand traditional networking like TCP/IP, which runs the internet, you can't just blast raw data. You have to wrap your data in heavy metadata envelopes.
I need a lot of overhead, usually.
You have to attach a destination IP address, a sender address, a sequence number so the receiving computer knows what order to put the packets in, and a checksum to make sure it isn't corrupted. If Gnosis just vomits bits onto the wire with no headers, no sequence numbers, and no lane assignments, how does the receiving end not just get a chaotic mess of static?
In a traditional system, you are absolutely right, it would be static. But prismatic refraction delegates the organization to the geometry of the content itself. The wire layer performs what they call deterministic content addressed lane assignment mid-flight.
Mid-flight. So the data packet figures out what lane it belongs in while it's physically traveling across the network. How?
It relies on a mathematical function called a 48-bit FNV1A content hash. Instead of attaching a bulky sequence number to a packet that says I am part 3 of 100, the protocol mathematically hashes the actual content of the data fragment, the shard.
So the data's identity is derived purely from what it is not, from an envelope wrapped around it.
Precisely. When these shards arrive, they naturally seek out mathematically compatible partners on the network based on that hash. When they find a partner, they refract and fold together into larger payloads.
So the geometry naturally snaps together.
Yes. And if a shard is corrupted or never finds a partner, it doesn't hold up the queue or crash the stream. It carries a gauge invisibility completion certificate and is securely vented away.
So it's like a self-organizing jigsaw puzzle. The pieces don't need numbers on the back. The unique shape of the cut guarantees they only fit in one specific place.
Exactly.
And to prove that this actually works under extreme stress, the architects ran an experiment called scrambled DNA.
If we connect this to the bigger picture, this experiment is the ultimate stress test of network resilience.
What did they do?
They took 1 megabyte of synthetic DNA data and combined it with 20 real highly complex cancer genes like TP53, BRCA1, and KRAS.
And then they actively introduced chaos. They scrambled the input byte order. They simulated a network environment where packets are arriving completely out of order, garbled by interference.
Right.
In a traditional TCP network, if you scramble the packets, the file is corrupted, the image won't open, the video is glitchy static.
But because prismatic refraction uses content-addressed hashing rather than sequence metadata, the Gnosis protocol perfectly reassembled all 20 cancer genes with 100% block count parity.
100% parity. The source explicitly notes that the KRAS gene, even when completely scrambled, produced the exact same settled byte multisets as the unscrambled version.
It's amazing.
The wire protocol is what they call permutation invariant. It physically does not care what order the bits arrive in because the geometry inherently knows how to snap back together.
And it does this without slowing down to organize the chaos. The average throughput across those 20 scrambled cancer genes was a pristine 6.61 megabytes per second. By delegating data integrity to geometry rather than metadata, we can fundamentally rethink network engineering. We don't need heavy packet tracking algorithms if the data naturally knows its own shape.
Okay, so we've solved the network bottleneck. But there is one final physical barrier. The software has to talk to the actual metal of the server. It has to talk to the Linux operating system. Let's look at the actual transport fabric. The primary engine here is the Gnosis Uring native transport.
This is where all the theoretical math hits the silicon. The Gnosis Uring transport maps the Gnosis primitives we've discussed. Fork race, fold vent, directly to Linux IRing kernel actions.
Let's slow down for a second because this is crucial. For someone who doesn't configure Linux servers for a living, what is IRing and why is standard communication so slow?
In a traditional web server, the software lives in user space, and the hardware is controlled by the kernel space. When your software wants to read a file or send a network packet, it has to ask the kernel for permission. This is called a system call or a syscall. The processor literally has to pause your program, switch contexts into the kernel, do the work, switch context back, and resume your program.
That sounds slow.
That context switching takes a massive amount of time and CPU cycles.
So it's like a worker having to walk across the factory floor, knock on the manager's door, ask for a tool, walk back, use the tool, and then walk back to return it.
Exactly. A work ring is a relatively new feature in Linux that solves this using shared memory rings, a submission queue, and a completion queue.
Rings, okay.
The user space software and the kernel share the same physical memory space, so instead of knocking on the door, the software just leaves a note in the submission queue. The kernel, running on its own thread, sees the note does the work and leaves the result in the completion queue.
So there is zero context switching.
Zero. It's a zero syscall hot path.
And what Gnosis does, which is brilliant, is map its geometric primitives directly to these queues without any translation layer. A fork primitive mathematically maps perfectly to a batch submission queue entry.
Yep.
A RACI primitive maps perfectly to the first completion queue entry wins, and the VE primitive maps directly to a kernel cancellation operation on the losers. The software is directly gripping the physical capabilities of the Linux kernel gears.
That direct physical mapping eliminates almost all modern web server overhead. And the throughput statistics prove it. They benchmarked 5.1 million requests per second for plaintext on a single node using just 8 threads.
5.1 million requests every second. That's absurd. But what about cold starts? One of the biggest complaints about modern serverless architecture is the time it takes a system to wake up from a dead stop.
Traditional environments struggle here. A standard Node.js environment takes about 85 milliseconds to boot. Dino takes over 1,500 milliseconds.
Wow.
A Gnosis subprocess takes 172 milliseconds, which is okay, but they completely bypass this with the node daemon.
The node daemon is a persistent process that keeps a tiny 34 kilobyte native C client hot in the background. With the daemon running, a cold boot takes just 0.7 milliseconds, and it achieves a warm hit latency of exactly 2 milliseconds. It effectively eliminates the startup penalty.
And when you compare this holistic system to an industry standard like Nginx, the performance gap is almost comical. For serving standard CSS files, Gnosis is 20 times faster. For serving JavaScript payloads, it is an astonishing 84 times faster.
84 times faster than Nginx? That doesn't even make sense. Nginx powers half the internet. How does it beat it by 84 times?
It's the combination of the iRing direct mapping and something called laminar codec racing. Remember Eve, the compression compiler?
Yeah, the Worthington whip.
When a request comes in, Eve races Jizit Brotli and deflate algorithms against each other on every single chunk of data, instantly picking the smallest one. Combined with their custom Eon Flow framing protocol, the metadata overhead is microscopic. Eon Flow framing overhead is measured at 0.0%. Standard HTTP 1.1 overhead is nearly 30 times higher at 0.89%.
It makes traditional web servers look entirely obsolete. And what's fascinating is the multi-transport fabric. The server can speak HTTP, TCP, and UDP simultaneously through the exact same pipeline.
Right, because of prismatic refraction.
It can receive fragments of data across different protocols entirely out of order, and the geometry just folds it all together perfectly.
When the software structure is so perfectly aligned with the hardware polling thread, you achieve a synergy that makes layered software architectures look incredibly wasteful. Gnosis doesn't just run on Linux, it physically aligns with it.
So with a framework this fast, this mathematically rigorous, and this tightly bound to physical constants, you obviously aren't just using it to serve a basic Hello World web page.
No, definitely not.
The final section of the source material reveals that Gnosis is already being utilized to build incredibly expansive, complex, real-world layers. We're moving from optimizing how quickly a server can send text to mathematically modeling human kinematics.
Yes. The source details a native eye-tracking corpus surface built into the source eye-tracking.svds module. It actively tracks calibration deficits, manages gaze formats, and handles persistence.
Eyeballs. How does a web server track eyeballs?
By treating the trajectory of a human pupil as just another topology flow.
Oh, wow.
Because Gnosis handles ambient law and geometries at a foundational level, it can unify physical data. Instead of different VR or AR hardware headsets forking their own proprietary messy gaze formats, they can stream the raw physical telemetry into the Gnosis semantic layer and let the mathematical proofs normalize it.
And it pushes even further into virtual reality with the avatar stack. There is an avatar.ets kernel that interprets VRM humanoid metadata. It solves procedural clip states and draws deterministic morph outputs. Basically, it calculates exactly how a 3D avatar's bones, joints, and facial expressions should move.
Right.
And it does this natively without relying on massive external 3D game engines like Unity or Unreal.
To the amplituhedron, there is no difference between calculating the most efficient way to route a CSS file and calculating the kinematic constraints of a 3D avatar's arm moving through space. It is fundamentally the same mathematical process, resolving geometry through the Fano plane.
It's incredible. We went from talking about optimizing web server requests to calculating the physical movements of digital humans. But the most expansive and frankly the most profound application mentioned in the text dives into ecosystem governance and consciousness itself.
The formal ledger we discussed earlier, the one using Lean 4 and TLA Plus to provide 14 mechanized proofs for server throughput, is being applied to community governance. They've built a formal voting surface.
A voting surface.
It uses theorem-backed logic to handle ecosystem voting rules.
It mathematically proves zero-deficit optimality and deterministic tie-break laws. It maps decision process pressure. Now, just to be very clear, for you listening, we are entirely neutral here. We are neutrally reporting on the architecture described in this document. We aren't taking a stance on the ethics of algorithmic governance or the politics of AI-driven voting systems.
We're just looking at the math.
We are purely looking at how Gnosis manages to map these incredibly abstract, messy human concepts into rigorous mathematical topologies. And it takes that abstraction to its absolute limit with what it calls the psyche twin reducer.
This is where Gnosis crosses the boundary from computer science into digital ontology. The source describes reducers for identity, metacognition, and psychogrind consciousness bundles.
Consciousness bundles.
They're literally modeling complex human states conflict, emotional exhaustion, deception, and even consciousness uploads using the exact same primitive basis of fork, race, fold, invent.
The potential here for a unified standard of reality is staggering. If an eyeball's gaze, a 3D avatar's physical movement, the voting rules of a massive community, and the metacognitive state of a digital consciousness are all subject to the exact same 14 mathematical proofs and thermodynamic constraints, then Gnosis isn't really a programming language.
It's something else entirely.
It is acting much more like a literal digital physics engine.
It creates a seamless continuum. There's no separation between the mathematical rules that govern the transport of a bit over a fiber optic wire and the mathematical rules that govern the resolution of a digital conflict between two avatars. Everything is unified under ambient law.
Okay, we have covered an immense amount of ground today. We started by tearing down the idea of linear text-based code, replacing it with the concept of code as a physical racing geometry on the Fano plane.
Right.
We explored how entire complex programs can be folded into 28-byte amplituhedrons that load in constant O of one time. We talked about vomiting bits onto a network and letting the content find its own shape through prismatic refraction.
And we saw how this all meshes perfectly into a Linux iron kernel.
To achieve speeds that literally push against the speed of light.
This raises an important question for anyone building systems today or really anyone interacting with digital technology. As the world grounds in information overload, and as our software becomes exponentially more complex and bloated, we're reaching the breaking point of human-driven heuristic testing. Gnosis offers a model where certainty is proven by math, not guessed by running benchmarks.
Yeah.
It suggests a future where we save enormous amounts of computational waste by relying on geometric inevitability rather than logical deduction.
And before we go, I want to leave you with one final thought to mull over. It goes back to the swarm of racing compilers and that concept of the void boundary.
Oh yeah, the boundary of failure.
Remember, the system learns exactly what doesn't work to form the boundary of its intelligence. Those 11,016 rejections in the forest passes physically define the exact shape of the system's success. Think about that for a second.
A powerful metaphor.
What if you mapped your own life decisions that way? What if your personal intelligence, your own growth, isn't actually defined by the successful goals you've deliberately programmed into your life, but by the exact shape of every failure you've allowed yourself to experience and vent? The actual boundary of your potential is carved by the things you've tried, raced, and ultimately ruled out.
The void boundary of a lived life. It is a profoundly beautiful way to look at the necessity of trial and error.
It really is. Thank you so much for joining us as we unpacked the architecture of the future today. Keep exploring those boundaries, keep racing those ideas, and we will see you next time for another deep dive.